Welcome back, guys. So, figured out my analog discovery issue. Apparently, what I thought was the official USB cable was not the official USB cable, even though they looked exactly identical. So, somehow I got them mixed up. So what I have on the desk here is my analog discovery plugged into the USB and also plugged into a 5-volt cell phone power supply with a 2.1 millimeter jack on the end. And I soldered up did a rough solder up of the interface device that we ordered last Sunday. While soldering it up, I was like, oh no, that was wrong, that was wrong, that was wrong. This is why we do prototypes. So let me show you the changes I made. Oh, I'm in the library. Okay. Yeah, so I need more than 2 ground pins. The max for the 5-pin that I think I'll need is 6, and that's what respectably fits. So we have 6 on TP1, which is 1 is always ground on miniPCBs. 2 is always V plus V, or positive DC power. So we'll just stay with 2. And TP3 is always negative DC source. TP4, this could be anything. So TP4 is generally going to be an input, and TP5 is generally going to be an output. What you see here is on the ground, I soldered an extra dual down here so I can get 4 grounds on this guy. So I got the waveform generator return, the power supply return, and then channel 1 and channel 2 of the scope returns, all on TP1. I have red, so positive DC supply on TP2. I have nothing on TP3 because I'm not going to use the negative supply. I have the waveform, what do they call it? Waveform generator 1 on TP4, and I have the scope 2 on TP5. Okay, and here on my desk I've got some prototype miniPCBs that I soldered together sometime last year, and basically I can take the miniPCB and I can plug it in like that, and then I can unplug it and I can plug in a different one. There we go. If I have hand-eye coordination, I could do it. There we go, like that. So that's the idea of this interface board, is that you can quickly change what's connected to your analog discovery. Yeah, so anyways. All right, so I showed you that. I actually already ordered this panel. Yep, I'm doing stuff without you guys. Sorry about that. So this is what the panel looks like in the preview. And if you come over to the datasheet that we were working on together, the Gerber files section where I have images that I automatically export from Eagle, or I export with a script. I haven't written the VBA code to automatically insert them in here, but that's my next step to get the datasheet so it's not so labor intensive. So I've got top copper, that picture. Here, we'll zoom out a little bit. So top copper, and then the image has like a little frame and title block. So file description, top copper, and then file extension, and that's the file name, but I call it DWG number or nomenclature. Top cream, empty, nothing on it. Bottom cream, empty, nothing on it. Bottom copper, got the part number here. Y'all may have noticed that I forgot to include the part number on Rev A, so I had to respin it anyways, and so it's no hassle to include the 6 pins since I was respinning it already. And top silk screen, bottom silk screen. So the part number is in both copper and silk screen on the bottom layer. Solder mask, bottom solder mask. Edge, so this shows the overall edge and then also the outline of holes. So maybe this should be called the board outline, but in Eagle they had a layer called edge already, so I just stuck with that. V-score, so those are your V-score lines here, 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 and here. And what that means, what that means is that there's a groove. Sometimes it's called V-groove. So there's a groove on both the top and the bottom of the board, and then you can take it and you can break it like a Kit Kat bar, like that. And then this guy comes off, and you could give this to one student, and then another student comes up, and you break that guy, and you give that one to that student, and another student comes up, and you break it, and you give this one to this one, and this one to this one. And so each panel has 5 pieces. So if you have 25 students, you'll only need to buy 5. Yeah, okay, yeah, you got it. You know to do math. Yeah. All right, and then the milling layer is empty because there's no milling and routing on this. And that covers the Gerber files. All right, so the next thing is, here's waveforms. So we can, let's see, give me a scope, right? And actually I should set up the power supply first. So welcome and supplies, positive supply. Let's set the positive supply to 5 volts. Just hit tab. And yeah, let's go ahead and turn it on. Sure. And then go back to welcome and wave gen. And let's have a sine wave, 1 kilohertz, period, 1 millisecond. Amplitude, 1 volt is way too high. This is what I'm going to show y'all is an amplifier. So we're going to put in 100 millivolts, so 0.1 volts. And the offset, we're going to have it 0. This particular mini PCB has a capacitor on the input, so it's AC coupled. So we're just going to leave the offset at 0 because it doesn't matter. And symmetry 50%, phase 0. That sounds good. Run. I don't know if I'm doing this all in the right order. It's been a little while. We'll go back to the scope and let's give us channel 1. Let's see. Okay. Just say run. Okay, now what we see here is there is no mini PCB plugged in to the interface device board. So what we're looking at is the orange is channel 1, and orange channel 1 is connected to the WaveGen output. So channel 1 is looking at what's on TP4, which is the input to the mini PCB. So this orange signal is what is going to go into this little amplifier mini PCB. And I would tell you the number, but I already changed my how I'm organizing the mini PCB collection. So this number is going to change, but this is a common emitter amplifier with an NPN transistor. So let's see. So I'm just going to go ahead and plug this in. Okay, what's up? Okay, so apparently if I touch that, that's pretty sensitive to noise. 500 millivolts per division. Okay, well, let's we'll leave it 500. I'll just plug it in and we'll keep going. But I need to open Fusion 360 and design a tray or a base, essentially a housing for this interface board. Maybe even something that contains the analog discovery as well. I'll work on that, but I have to buy a subscription for Fusion. So let's see. All right, so I'm going to plug this in, and what you see is channel 2 becomes active because now it actually has a signal that's non-zero, and we need to drag this guy. We'll drag this guy, say, down to here, and then you can actually come over to the side and you can scroll with your roller bar. You can scroll and it will zoom in or zoom out, which is pretty cool. I think you can, you can come down here and you can scroll on the time. That's pretty cool. On the yellow, I need to select the yellow, then I can scroll the yellow. Okay, so we'll leave the yellow like this, and then blue. Notice how blue is not centered. So yellow is here. This is 0 for yellow, and blue is here. So this is 0 for blue. And yellow, it goes on the negative side, and then positive side, and then negative side, and then positive side. But the blue is always positive. There you go. I lined them up for you. Y'all were probably asking me to do that. Except I can't click on the yellow then. Let me zoom that back out and put this back up, and then okay, I need to make here, so that's that size. Okay, and then we'll make them the same size. There we go. All right, cool. So now we're lined up and we're on the same scale. Well, why does this guy say, why did that not change? So if I say 2, 200 MV. Okay, and then why is this not 200 MV? It's weird. I kind of want them to be the same. Okay. 2 volts. All right. So if I put this guy at 2 volts, sorry. If I put this guy at 2 volts, okay, the trigger, give me my trigger. Where's my trigger? So mode, auto set, source, channel, rising, level. We'll put this at 0.05 for 50 millivolts because we know that the orange is 100 millivolts. Why is that not? Okay, we'll switch to channel 2 because I know we have a good signal for that. And we're going to put this at 2.5 volts. Oh, 2.5 volts. Okay, so this is the trigger right here. And that's set for channel 2 as the source, edge type, rising edge, and the level is 2.5 volts. Okay, cool. So these guys are on the same scale, same. Right, so if I look here, I have 2 volts. And if I click on this guy, move back up, I have 2 volts. So if the amplifier had a gain of 1, it would just be a buffer, an analog buffer. And blue and yellow would be the same size. But since it's an amplifier and it has a positive gain, the output is larger than the input. Well, I guess I shouldn't have said that because it has a negative gain, but it has a gain larger than, with an absolute value larger than 1. So anyways, yeah. Let's see, where's my little screwdriver so I can adjust the potentiometer for you guys? Here, this will work. So I have a potentiometer on this mini PCB, and it lets me shift the, I need a better screwdriver. Hang on a second. It's not the first time I've opened it. I just keep them in the package. Okay, so can adjust this potentiometer, and it adjusts the bias voltage on the base of the transistor. So you can play with it and go, oh, okay, well, that's what that guy does, and 100 millivolts is too big because we have distortion up at the top. So I'm going to go back to the wave gen, and we're going to make this like 20 millivolts. So 5 times smaller. We'll go back up. We'll go back and look at the scope. That's a little better. And then, yeah. Okay, cool. So what you see here is when I turn the potentiometer, I'm moving the signal up and down. I'm not changing its size. And notice this vertical line right here. This is the trigger line. So that's where this guy right here and that line right there, the blue will stay on that line because that's where our scope is triggering. You can see it. That's why it shifts to the right side or to the left side. And when I go too low, it stops triggering on it, and it starts to get crazy because it's not triggering on the signal. You're just watching it all go by. But here it triggers, and it's like taking a picture at that moment. And then we can go too high, and now it's weird again. We go lower, and since this little board has a 5-volt supply, 2.5 volts is halfway between 5 volts and ground. 5 divided by 2 is 2.5. So if I set my signal so that it is pretty much centered around 2.5, then yeah, only good things can happen. Yeah. So yeah. So again, the yellow is the input and the blue is the output, and these are set to the same scale. So what you can see is that the blue is significantly bigger than the yellow. And just for entertainment, we'll zoom in and this is the yellow, and that's the blue. Notice how when the yellow is going up, the blue is going down. That's because this amplifier is actually inverting the signal. So it's a negative gain. So instead of gain of, well, let's just calculate the gain real fast. Measure. Where's my measures on the scope? Measurements. Add custom channel. Channel 1. Name, channel, precision, what? Cancel. Add, define measurement, channel 1, vertical, peak to peak. And add, channel 2, peak to peak, and add. And then can I do like a math? Just to give me the gain. Probably, yeah, right? But close. Okay, so what we have here is we have 1.7 output and 43, well, 1.7 volts as the output and about 40 millivolts on the input. So if we pull up the calculator and we say 1.7 divided by 40, because I set my function generator to be 20, so 40, yeah, equals, well, hang on a second, 1.7 divided by 0.04, and that's 42.5. Now if I say 1.7, no, I'm not gonna. I'll just leave it at that. So this guy 42.5. So this mini PCB amplifier has a gain of negative 42.5. Now I can. So let me close this. So I can just unplug this mini PCB and plug in a different. Now this should have a similar one because it has similar values. This should just go. This should just work. My potentiometer must be all the way to one side. There we go. What? What did I do to this guy? Maybe it's broken. Okay, well, let's try a different one. Plug in this guy. Okay. Well, this is weird. Huh. That was weird. Is weird. Okay, well, we'll play around with that guy later. I experimented with different transistors when I soldered those up. Wow. Did we just get lucky on that first one? Wow. This is cray-cray. Let me plug that first one back in. Yeah, right where we left it. Okay. Well, let's go try a different one. Okay. Still looks weird. think I need to lower my input signal still again or whatever. Okay, let's go back to the wave gen and let's set this to 10 millivolts. So now that's even lower. Now can I adjust this guy where it makes sense? Nah, not super great. Let's see, I'm going to drag that guy down here, this guy. So, see some crossover distortion, it looks like. Okay. Wasn't expecting these to be so weird. I was expecting them to be like the first one. Wow. Just wow. Really? Oh. Well. So that first one is the only one that has filter capacitors soldered into the onto the miniPCB. Surprised if they used to be working great. It's weird though. Okay. Nah, it's not that, doesn't look that great, but so this is just one of the other ones, right? 2.1 and then about 20 millivolts. So we can pull up the calculator. There, calculator. What? Ooh, Mary Shelley. Who cares? Calculator. Okay, so we're going to 2.1 divided by 20 millivolts divided by 0.02. 105. Wow. Wow. 105. Whole gain of 100. That's cray-cray. No, I think I do remember trying to get a gain of 100, but anyways, it looks like we got a lot of distortion with gain of 100 when we had a gain of what was it, 42, like that. That's clean. Where was the calculator again? So my gain went down. This is weird. Anyways, 0.9 divided by, oh, of course the gain went down. Well, not the gain. The output went down because the input went down. So 20. Is clear. 0.9 divided by 0.02. 45. Right. So gain of 45. So gain of 45, nice and clean. Gain of 100, lot of distortion. See, there you go. I just touched a common emitter transistor amplifier, played with the bias potentiometers a little bit, the analog discovery, and now not only can I theoretically tell you that, hey, a single transistor amplifier, you start to get up around gain of 100 on these components. Different transistors and resistors and layout will behave differently, but with these components in this layout, you get up around 100 and you start to experience distortion. That's what it's all about, though. So, yeah, kind of cool. And so then what I want to do is I'm not going to do it today because this is about to be revised anyways. But when I do revise these miniPCBs and create the data sheet for them, I'm going to take screenshots of what I do here and put them over in the datasheet in a report section. So you'll have a design example, and it'll tell you like target value is 5 volts, upper limit is 5.1, lower limit is 4.9. I don't know. Yeah, I'm making this up at the moment. 4.9, whatever the analog discovery 2 specs are. This is not applicable, so I would just delete that for this one, for this example. Peak to peak, right? Signal voltage. So target value, the input is 0.02 volts, because we're in units of volts here. Lower limit 0.17 and 0.023. That it looked like I was seeing numbers like that, but maybe I'll make it be like 5 millivolts or whatever the analog discovery 2 says. I don't want to be outside that. Signal frequency 1 kilohertz, right? So anyways, I'll fill that stuff out, and then I will put the performance characteristics that I measure, and then you'll have the part numbers that I used, the description of the part number of the part, and then I will kind of list, I'll list the tests that I'm going to run, and then I will run the test, take a screenshot, and put it in the data sheet. So you should be able to take the miniPCB that this is the data sheet for, use these design inputs, right? Basically use these parts, and run the tests I ran and get similar results. And that's what engineering is all about. If it can't be duplicated, then it's not science. And if you can't make it in a form factor that people want, it's not worth paying an engineer to do it. And if the engineer can't design it in so it can be manufactured with a certain cost at a certain rate or volume, with a certain quality level, then it's not worth engineering. So yeah, so anyways, so yeah, okay, enough of that. Let's see. So that's probably all I want to show you in this video. Basically, we soldered up one of these guys, and then we came in here and revised the interface device board to be revision B, and we already ordered it, so that's on the way. So the next thing between here and just blitzing through a bunch of mini PCBs is I want to put a little bit more automation into the datasheet to take out some of the time just spent clicking to insert pictures. And then I'm probably going to come down to this test plan section, design example, basically from here to here, from design inputs down to developmental tests, or excuse me, test report, per example. They don't feel right. So basically everything above feels good. So theory of operation, so your name, detail table, theory of operation that I'll insert, pictures of the panels, pictures of the single board, images exported from CAD showing where the components go, a screenshot of the schematic, an image of the schematic, the Gerber files, and then that's where my uncertainty starts. So a little bit more datasheet editing, some Visual Basic automation, and we should be ready to just blitz through a bunch of these mini PCBs so you can get them by Christmas or whenever y'all want to get them. the beginning of next semester, spring semester. Probably sounds good. Yeah. We're going to start with amplifiers because that's a good place to start, with just an analog signal in and an analog signal out. Yeah, kind of cool, huh, guys? All right, well, I think I'm going to end the video here and post it and keep plugging away on the data sheet. Maybe I will work offline, or should I show y'all what I do? Well, still trying to figure it all out. Anyways, thanks for checking out the video, and looks like we're getting closer to having a functioning mini PCB system for you guys. So, all right, later, guys.